Hi everyone, we are back and we are going to finally talk about fracture. So, fracture is it's our section 3, regime 3 of our stress strain curve. And it is exciting because things break, and when things break, that's cool. But also, and actually, very importantly, it basically fractures the last resort for material deformation. So, after all other elastic plastic mechanisms are exhausted, the material will fracture. And materials, again, if you calculate the theoretical stress for fracture, it's orders of magnitude higher than the actual fracture stress. And why is that? Well, you guessed it, defects. And Frank Stallone. There's real life, again, in real materials, there are micro cracks. So when you have a micro crack in your system, and they could be nanometer, micrometer, but they basically function as stress concentrators. So when we apply an overall stress, sigma naught, to our system, near these micro cracks, the stress effectively increases, and it increases almost exponentially. It's a significant increase. And so that's why materials will fail at stresses much lower than the theoretical fracture stress. So how do we figure out when a material will fracture? Well, we can actually try to approximate that behavior by looking at a fairly simple energy competition. So why does my material want to fracture, or what energy contributions push a material to fracture versus not fracture? Well, if I fracture, the penalty that I have to, so let's say we have state 1 where we remain intact versus state 2 where we go to fracture. So if I go from state 1 to state 2, the penalty that I have to pay is I've created 2 new surface areas. So I have created surface area in my system that is always energetically very unfavorable. So I don't want to create surface area that is energetically unfavorable. I have to pay a penalty for that. So to fracture, I have to pay this penalty, but in exchange, I've relieved the elastic strain energy in my bonds. Because I'm pulling my bonds, I'm stretching my bonds in my potential energy curve, I am going from this state where my bonds are nice and at their equilibrium state to this state here where they are far apart. So to go from here to stretch, I'm increasing the energy in my system. So we have to figure out the energy balance of when this energy to create the surface area is equal to this, that's when my material will fracture. So let's calculate this contribution. So to create a surface area, I'm basically going to assume that this little crack is going to extend. Now again, my material has some thickness in this direction, some thickness here. So my crack, I could just basically approximate that area as, again, there's kind of 2 surfaces here. So 2a times t times 2, top and bottom, right? So I could approximate this area to create that surface. So I can just, even though it's an ellipse, I can just kind of assume, it's like this. It's through the thickness, so it's going to be 2a, and then again, so this surface here, through the thickness, top surface here, and that's going to be essentially that surface area that I create. Again, going into the board effectively here. So I'm creating this area, and I'm creating that bottom area as well. So 2a times t, hopefully that's apparent. So this is going to be my area, and I'm multiplying it by gamma, which is not my engineering shear strain. It is my surface tension, and that has units of joules per meter squared. So we see that A and T will have units of meter squared, so it's an energy term. Similarly, we can calculate the elastic strain energy in our system. And so if we were working with basically uniaxial tension, for example, we know that we can represent the relationship between stress and strain as such, and we integrated from 0 to our strain at yield this function as a function of dE. So we can actually calculate that. So I can just substitute it in E, and if I integrate this function, let me just erase this here. If I integrate it, and it's been some time since I've integrated, E epsilon squared over 2, and now I'm going to plug in, because I want it as a function of the stress that I apply. So I'm going to plug in that my strain is equal to stress over E. Correct. So I'm going to plug that in. So I'm going to be left with stress squared over E2. So that's what I'm left with. But now I need to take that and multiply it by an area, because this leaves me with a Pascal in terms of my units, which is a Newton per meter squared. And actually, I need to multiply it by a volume. So I need to multiply, which makes sense. I need to integrate the curve and multiply it by a volume to get an energy unit here. So I'm going to multiply it by that little elliptical crack. I need to multiply it by the full volume. So it's going to be basically, I'm just going to kind of assume it's like a, it's like a cylinder. Pi times the full diameter was 2a, times a squared times my thickness, which we see here. You'll also notice that we determined this to be positive because, again, that's energetically unfavorable. Well, here, our elastic strain energy is, we want to reduce that. That is a favorable interaction as we go from one step to another step. So this is my energy penalty to fracture. This relieving that elastic strain energy is negative, so it's going to lower my energy. So we're going to set those equal to 0, solve, and we get an expression for stress as a function of basically a critical crack size 8. And this is our Griffith criteria for brittle fracture. So this equation only holds for brittle materials. So ceramics, things that are extremely, extremely brittle, glasses, like those types. So ceramics, glasses, that's pretty much it. So this is our expression. So depending on the critical crack size, the stress for material fracture can change, and vice versa. So if I apply a given stress, I can look at the crack size required for that material to fracture. Now, this is a great derivation, but we've left out one important thing. We've been looking at just that this crack is just going to kind of extend perfectly every time that I apply, when I apply this stress. So I'm just going to break bonds. But we know at this tip, we're not going to break bonds initially. We're going to yield first. So that's why this is not a good criteria for ductile materials. So instead, Orowan, who, if you take another course in advanced mechanics, you'll hear a lot about in terms of, he was one of the key figures to kind of discover dislocations and how they contribute to mechanical properties. Orowan developed a very similar criterion. We're not going to go through that derivation. It's a lot more complicated, but very similar form, except now we have this parameter G sub C, which is the strain energy release rate. And this is an appropriate criterion for polymers, metals, and other materials that basically fracture ductily or not as brittle. Finally, there is one more way that we can kind of assess or actually determine or calculate essentially the stress required for fracture, and that's using our equation for fracture toughness. Now, this is an empirical, evidence-based basically criteria. So you have an applied stress, a critical or a crack size, and this K sub C is a material property. F is a geometric constant. We're just going to typically set this to 1. K sub C is a material property, and that's the fracture toughness of the material in one of these 3 crack modes. So you could look up this material property and then determine with this applied stress what's the critical crack size, or with if an initial crack size, what would be the stress required to fracture. So that's how you can essentially make sense of that material, or that equation, excuse me. So next time we're going to get into fatigue, and that will end our comprehensive study of the mechanical properties or mechanics of materials. So we'll see you then. Thanks. Bye.